Okay, so chapter 6. What happens when you have to deal with a non-orthogonal basis? So up until this point, we've had some localized orbital basis, and we've always, everything we've sort of derived, all the expressions we derive are based on the fact that these guys were orthonormal. Now we have to deal with a basis that is not orthonormal, and this integral gives you something. It's called the overlap matrix, and it's always denoted by S. And so any DFT code that uses a localized orbital basis, this is going to be true. It's not going to be orthonormal. Any quantum chemistry code, and the quantum chemistry codes always use localized orbital basis sets, they're going to be non-orthonormal. And so you have to just be familiar with, or say if you're using a Huckel Hamiltonian. That's a non-orthogonal basis set. So all these use non-orthogonal basis sets, and they've all been combined with Negev. So it's good to have some understanding of what changes when you're dealing with a non-orthogonal basis set. So, as usual, we're going to be expanding our wave function in terms of our basis, so that doesn't change. Right? You expand your wave function in terms of your basis, and then you put this into Schrodinger's equation, right? H psi equals E psi, and then you substitute in that sum for psi. So we have sum over I. I'll pull the E to the left-hand side, so E minus H alpha I times Ci. Right, that's just H psi equals E psi, where I wrote psi as that linear combination, Ci alpha I. And then you hit the whole thing on the left with alpha j, like we always do when we're dealing with an ortho, to turn it into a matrix vector equation or an eigenfunction equation. And then what we end up with is sum over I E times the overlap matrix S Ji minus H Ji acting on Ci, multiplying Ci is 0. And so that's your new eigenvalue equation. It's your generalized eigenvalue equation. In matrix form, that's just E times the overlap matrix minus a Hamiltonian matrix acting on the vector C equals 0. So this would be your overlap matrix and your Hamiltonian matrix and your column vector C. So that's what your eigenvalue equation becomes. It becomes a generalized eigenvalue equation. And that's what's solved in all these, well, it depends. Codes do it in different ways. But with when you're dealing with a non-orthogonal basis, this is what you end up with. So the DFT codes, you're primarily just calculating an E versus K relationship. In a periodic crystal, and to do that, you have to go into a block sum basis, just like what we did in 208. And so you define an alpha I of K as a block sum. Sum over all your unit cell vectors, e to the I k dot r, alpha I comma r. So alpha I is like your orbital index, r is your unit cell index. So the sums as usual over all the lattice vectors r, corresponding to the n primitive cells in the crystal. And then these matrices are defined in the same way, but now, just as we had an H of K before, you have both an H of K and an S of K. Again, it's the same matrix vector equation, but now these are all the matrices and that vector are functions of K. And so that's how you would generate your EK. You do this just as we did before for each K. Before we were just constructing H of K, and now you also have S of K. So S of K would just be, S of K would just be the overlap of two of these orbitals of K, like alpha I of K, alpha J of K, an overlap of two of these block function orbitals. Usually, in almost all cases, your orbitals alpha I are chosen to be real. Right, so alpha I is real, which means that for K equals 0, S I J equals S J I is symmetric, or I guess another way of saying that S transpose equals to S. That's because for K equals 0, all your block functions are just real. They're real. And for K not equal to 0, then S is going to be for Hermitian. Because then these, the block functions become complex. Simply due to those phase factors, you're multiplying them by the e to the I k dot r. Okay, so that's all about sort of the 208 level of what happens when you go to a non-orthogonal basis. You have to solve this generalized eigenvalue problem to get the EK relation. Okay, now what about if you want to then do something, implement your Negev algorithm? So for Negev, the equation for the green function becomes E S minus H. These could be functions of a transverse momentum minus sigma acting on G, your retarded green function. So the only difference between, before and now is this overlap matrix multiplying E. It's the only difference. H is still going to be the matrix elements of your localized orbital basis, whatever they happen to be. We'll talk about what sigma is in a moment, how it changes. But if you think about S, you know, so what, again, just S is, so S I J is alpha I, alpha J. And we always partition our device, you know, so that you only have matrix elements between I and J, and there's nothing between I and K because we want to keep it nearest neighbor. So we make these regions big enough so that there's no overlap by definition between, you only get nearest neighbor. So, you know, this may be 4 or 5 atoms thick, but we define that as one layer so that our Hamiltonian keeps its block tridiagonal form. And so that means that, you know, E times S is going to have both block diagonal terms. It'll add something to the diagonal, and it'll add something to the upper and lower off diagonals of this block tridiagonal Hamiltonian. So it's going to modify the T's, what we have been calling the T's, the coupling matrix elements will get modified also. The upper, right? We're setting up this Hamiltonian, so you got the diagonal and then the upper and lower diagonal. So both the upper and lower diagonal are going to get modified too by this ES matrix. And so what that means is that, I mean, modifying the diagonal term is trivial. You're just adding onto the diagonal. That doesn't really affect anything. But the off diagonal, what that means is that we define a new off diagonal block term. T tilde is equal to the actual off diagonal element. So this T would just be the off diagonal elements coming from the Hamiltonian matrix H. So these are coming out of H, the matrix elements of H, minus E times S L plus 1. These extra ones coming from the overlap matrix times the energy. And so you basically have these energy dependent matrix elements now. And I guess just for completeness, right, this is so trivial I'll never even talk about it, but your diagonal elements would also become your what we formerly called the diagonal elements, which are just coming out of the Hamiltonian, minus E times the diagonal block of S, right? Let me make sure I got E minus A. Yeah, that's correct. And again, this is just coming out of the diagonal block of H, and this is the off diagonal block of H.
SS is 1, right?
What's that?
ln, this value is 1.
No, not this time.
So what are we saying?
The actual, yeah, but I'm talking about block diagonal. So the actual diagonal elements are 1. But the block diagonal, because we define blocks as like multiple atoms, so you can have different atoms within the quote diagonal block. So for example, if you define, if you have 2 atoms per block, like your anion and your cation, and you call that your block, then it's not going to affect the true diagonal elements, but it will affect all the, you might get, you'll get matrix elements between the anion and the cation that all are part of the diagonal block. So normally, if right? Normally our D for our anion and cation would just be like, you know, ES, EP, EP, EP. That'd be your, say, I don't know, cation, anion block. And then another set, oh, let's just say we got two atoms, both the same, ES, EP, EP, EP. This would be like atom 1, atom 2, and normally that would be all you would have. Everything else would be 0. But now you'd have a bunch of overlaps here, part of your diagonal block. Possibly you could have them in here. I don't know, depending on how these are defined. They could be on the same atom orthogonal, but just definitely not orthogonal between two different atoms. And that's your D, so this would be like your DLL block, or DLL tilde. I guess this is minus ES, right? Minus ES, we go in there. And then the block next to it would be this P minus ES over here. Okay, but once we define these tildes, then everything looks pretty much like what it did before. All our algorithms stay the same as long as we replace everywhere there was a T with a T tilde. So as long as everywhere we had a T before, we'd replace it with this T tilde. So for example, your self-energy, due to the left contact, would now be T10 minus E S10 acting on my surface green function at 0 times T 01 minus E S 01. So, you know, just up front for each energy, you define a T tilde, and you use that everywhere you would have used your T before. And your surface green function itself, for example, G00, and say setting up for the dumb iterative algorithm would be E S00 minus or plus I eta I minus H 00 minus T tilde 0 negative 1 G00 T tilde negative 1 0 inverse. I think we played around with this eta too. When you think of throwing in a constant term, then you would pick up, you know, in a non-orthogonal, it just becomes I eta times the overlap matrix. I think we tried various things, but just keeping it on the diagonal still seemed to work fine. Otherwise, it becomes part of the T's also, right? Just like the E. The E became part of the T's. If you take the overlap of a constant, you just get back the overlap matrix element. And then, so you've got your sigmas. Gamma doesn't change, is still defined the way it was before, I times sigma r, or sigma, minus sigma r dagger. That doesn't change. The expression for your current doesn't change, or transmission coefficient still remains. It's like gamma 11, G1n, gamma nn, Gn1. RA. That doesn't change. Okay, so that's all good. Now let's talk about the electron density. That gets tricky. So if all you need is a current, it's pretty straightforward. Every algorithm you've done holds. You just replace T with T tilde. Wherever you had an E energy before, it becomes an E times S. And everything holds. Your expression for the transmission coefficient remains the same. Charge density. So let's talk about charge density. So let's go back and think about our scattering states. So I have my left injected scattering state, which is just going to be where the phi's on my non-orthogonal basis. Right? So nothing special here. I'm just expanding it in my non-orthogonal basis. And so if I write that out, that's equal to sum NM C N L C M L star phi M star bar phi N R. And the same thing, I'd have the same type of expression for the right injected spectral function, the same form. The same type of expansion, just replacing the superscript left with right everywhere. Right? So replace on the C's the superscript left with the superscript right. Okay, now I want the charge density resulting from, we get the charge density by summing up the contribution for both the left and the right. So let's look at the contribution of the charge density from the left injected wave. All right. So N left would equal the sum over K left of psi left squared weighted by the Fermi factor. I'm going way back to chapter 1. So these C's are just the green function times a gamma. Sort of redoing the derivation we did very early on in chapter 1. And everything goes through pretty much. So if I write out, NL of R is 1 over N sum KL sum NM CNL CML star phi M star phi N F of E KL minus mu left. And then you replace the C's by gamma 1 1. Let's see if I get this right. GN1 gamma 1 1 for that guy, and the other guy becomes GM1 star gamma 1 1 for the other guy, for this guy. And then we do what we did you replace this guy by, you turn that guy into an integral, and we have some NM phi M star phi N A integral dk over 2 pi G N1 gamma 1 1 G star M1 gamma 1 1 F. We convert this guy into an integral over energy, integral dE, it becomes integral dE over 2 pi A dE dk inverse times all the other stuff that we already have there. And so dE dk inverse is, this stuff all becomes, I guess, A over H bar times the velocity, the left injected velocity, which is like, I think, 1 over gamma, which kills off one of the gammas. This is exactly what we went through way back in the beginning of chapter 1. So the final expression is, the only thing different now is we've got this sum nm, these two wave functions, or orbitals, let me say orbitals, integral over energy gr, I'll just leave off the superscript, gn1 gamma 1 1 G star 1m F of E minus mu L. And this thing is just our left injected spectral function, right? This is our left injected spectral function times the Fermi factor of the left lead. Except, if you notice now, I have an M here and an N here, which is, that means it's the off-diagonal element of my left injected. I'm no longer getting away with just having the diagonal element. And I have this M here and an N here. And the reason is because this basis is no longer orthonormal. The other thing, this is N of R, and due to injection from the left of R. We've never, I kind of swept it under the rug. We never really had N as a function of the position vector R. We had this approximate thing, up until now we just evaluated the spectral function at site J and divided by some volume associated with that site, well, the spectral function times F. Right? The spectral function times F, integrated it, site J, and divide by some volume associated with that site. So we had, some like A, J, J, F, and we'd divide by some lattice constant or something out front to get the charge density. Right? We never really had something that was a function of position, true position. It was some approximate expression associated with that atom J. But now we really have, in like these DFT codes, they really do know the, the functional form of their basis sets. They do know what they are as functions of position. So if you want the charge density at any given true position, you can have it, because you know the functional form of these phi's, and this is how you get it. And so many of these DFT codes, to calculate the charge, they actually implement a real space grid and then evaluate this expression. They don't do it using negative. You would if you're doing it. Evaluate this expression on the real space grid and then send that real space, if we were going to then follow up by Poisson's equation, send that real space grid into Poisson's equation. And in that way you can really take into account things like the polarization of the actual atomic wave functions due to potential. You can actually see how the orbitals might change due to various potentials. For us, the orbitals are sort of rigid, and we just get this total number associated with the charge of each atom. Okay, but to implement a real space grid is really numerically painful, and the codes that do it, like Siesta, for example, it's computationally intensive, and so therefore, there's always this trade-off between sort of accuracy and the difficulty of the calculation and the time it takes to do the calculation. So Fireball did not implement a real space grid. It used an approximate form for the charge, just like this over here, except you can't do this if your basis set is non-orthogonal, right? This is not sufficient. You got to do something other than this for a non-orthogonal basis set. But before I do that, so the total charge, we got the left injected charge. The right injected charge has the same form, and so you add the two things together, and you get that n of r is equal to sum n comma m phi m star of r phi n of r times integral dE over 2 pi what we call this electron correlation function G sub n superscript n comma m of E. Right, this electron correlation function was just this. You had this term here underlined in blue, weighted by F, plus the same term coming from the right injected spectral function weighted by the Fermi function of the right. You sum those together, and that was what we called this electron correlate, because that was what before, was giving us the electron density. So that was our G superscript n that I wrote here. Now this thing, I may have mentioned it in passing, this is nothing other than your density matrix. The integral, when you integrate it over all energy, that's your density matrix. So a very compact form for this electron density as a function of position is a sum over your non-orthogonal basis times rho and m. And so, I don't know, if you've read any of the articles, probably not. It all came out during the 2000s, the molecular electronics era. But people would talk about, they would use, say, Gaussian, for example, like the Purdue group combined Gaussian with negative. So you'd use the Gaussian or the DFT code. Oh, here's how it worked. They would use, the way it was described, they would use negative to get the density matrix. and then they would send that back into the quantum chemistry code or the DFT code, which would then calculate the charge and provide, create these new functionals and update the Hamiltonian that would then go back to negative like that. So normally the way these codes work is you have your DFT, and all it does is calculate, how do I want to say, all the eigenfunctions of the Hamiltonian. And then it goes ahead and it does an equilibrium calculation of the charge. Does an equilibrium calculation of the charge. So this, is a non-equilibrium quantity because it has buried in it both an F left and an F right. And so they would replace I can't think of exactly how it worked, but replace the calculation that the DFT code is doing to get the charge with this calculation coming out of the negative equation. Now, in something like Fireball, as I said, they purposely chose not to have a real space grid because it takes time, and they wanted something very fast. And so they had to come up with some approximation like this, like this over here, that's valid in a non-orthogonal basis. And there are approximations. So there's two approximations for local charge. So we want some way to calculate the local atomic charge in a non-orthogonal basis. I mean, you're asking yourself, when you think of it, you've got some kind of wave function cloud if you've looked at molecular, pictures of molecular orbitals. And now you need some approximation to say, okay, how much charge is associated with each atom? Because that's what you need when you're going to send it off to Poisson's equation, for example. And there are two well-known approximations for this that are most probably well-known among quantum chemistry. One is called the Mulliken charge, and the other is the Loden charge. I mean, both are kind of approximations because it's really not a well-defined concept to just divide up charge. This much charge goes to this atom. It's kind of qualitative. There's no real hard and fast way. The only thing that's truly exact is if you just calculate the charge as a function of position, and then it is what it is. This has got to be sort of approximate, and it is. So let's look at the Mulliken charge first, since that's the easiest to understand. So if we look at, going back to our expression for just n as a function of position, and I'm going to break it up into both atoms and orbitals as sum. All right, so let's see. So the orbitals, the atoms, so these are atoms. These are my orbitals. If we, okay, so to get the number of electrons associated with atom A, you do the sum over all atoms B and all the orbitals, okay, but not over A. So we do the sum over all B, I, and J and integrate over position. And when you integrate over position, those two wave functions just become the overlap matrix. when you integrate over position, those two 5's just become your overlap matrix. So you end up with N, the charge, number of electrons associated with atom A, I'll put a big superscript M for Mulliken, is equal to sum over all other atoms B, sum over I comma J. And that would be the approximation for the Mulliken charge. And in an orthonormal basis, S is diagonal, right? In an orthonormal basis, S is diagonal. And so this would just reduce to exactly what we had before. Just the integral over, this would just become rho AI, which is just the integral of that G superscript N, your electron correlation function, AI, which is exactly what we had before. And the sum would be the trace over all the orbitals, which is what we always put in there. The trace over all the orbitals, integrate over energy. Gives you the charge on the atom. So this is like just a number, right? And then to get what we had before, if you wanted the density, you need to divide by a length or volume or area, whatever kind of geometry you're using, to go from just a number to a density. So before we had, we divided by 1 over A in a 1D. To get a density, this would be per unit length, because this is just a number. Number of electrons associated with atom A. And I guess I'll just write it down. So the load and charge is, I'm not going to even try to derive it, it's not worth it. We don't use it because for us it's very, we can't use all our favorite algorithms if we wanted to use this charge. So these are my atom indices, these are my orbital indices, and you can see immediately why we don't like it. This is the square root of the overlap matrix, and this is really the square root of the matrix. And these are the indices of the square root of the matrix. With our density matrix sandwiched in between B prime, J prime, and then another overlap matrix square rooted. So that would be the load and charge associated with atom A. Fireball, the Fireball code implements both. By default, it seemed to go to the load and charge, but once we integrated it with Nega, we started using exclusively the Mulliken charge. We did a lot of tests calculating both charges, and we never found any difference for the systems we were using. And so we stuck with the Mulliken charge, and we'll have to finish off this next time, because even with the Mulliken charge, you can see that you need, the off-diagonal elements. And when you need off-diagonal elements, it means that this recursive green function algorithm has to be modified, because now you need not just the diagonal elements in the first block column, but you need the diagonal elements in the first off-diagonal elements to do this calculation. So I guess the next Monday is Memorial Day. So that's won't be a class. We can have a discussion Friday if you want to discuss the homework. Although if you want to leave early for Memorial Day weekend, that's fine too. So we did discuss homework quite a bit in the last lecture. Maybe it would be sufficient. And since there's no really fixed date, I would like to have a few days before grades are due, so I have time to look at it. Right. So, do you think okay? Let's have a vote. Do you want to have a discussion this Friday or not? Yes. Yes. No. Yes. Okay. We'll have one. We'll videotape it. Can't make. All right. So 1:10. 1:10, because I have that meeting always from the noontime meeting for the DOE grant. So 110 Friday. All right, sounds good.
What is the deadline for homework 2?
Well, sometime during finals week, preferably give me a few days to grade it. Because, you know, grades are due Tuesday.
Sorry, yeah, you have like assigned another homework.
Yeah, you can just turn it all in at the same time.
Okay.
So just, you know, it's like it's going to be a lot of grading. So just give me a few days to grade it because grades are due on Tuesday after finals week, I believe. Tuesday noon. So, you know, give me a few days. All right. That's it.